It's an honor today to introduce Professor Dr. Andreas Liese. He is the head of the Institute of the Technical Biocatalysis at the Hamburg University of Technology, an award-winning professional in research and teaching activities like the award for up-and-coming teachers in higher education, the KEMA. He has several books and books contributions, several patents, and nearly 170 peer-reviewed journal contributions. So he has great experience in bioprocess development, including characterization and optimization of biocatalytic processes, reaction engineering development of bio and chemocatalytic reaction sequences, non-conventional biotransformations, smart bioreactors, and online analysis and processes control of chemo and biocatalytic processes using Fourier transform infrared and fluorescence spectroscopy. Dr. Liese visits us today to share his knowledge thanks to the collaboration of the Universidad Nacional. So we also thank them to make us part of this great opportunity. And now I leave you to Dr. Liese to hear his words, and thank you all of you very much for joining us today and for your attention. Thank you.
Yeah, thank you very much. Thank you very much for inviting me over here to give you a lecture this morning and to spend the day here at the Tech. And also thank you to the UNA who enabled me to coming over here. Yeah, and I was asked to give a student lecture this morning. And so the topic I've chosen is bioreaction engineering enabling biotransformations. What I would like to do with you the next hour is to introduce you to bioreaction engineering. So what are the key points, the fundamental principles? Just the fundamental, not principles, not to go too deep. And you're also able to participate in the lecture. So we run an online quiz. So if you have any mobile device with internet along, you can participate in a moment. Well, I structured the lecture in that sense that I will start up with an introduction. Then I will discuss with you these terms of conversion, selectivity, and yield, which are crucial to differentiate and to apply them to interpret any data. And then the second part of the lecture will be basics on continuous bioprocessing. So the different reactors that you could choose, which one you want to choose, and how to operate them. Those we are discussing in this lecture, and I will end up with a take-home message. Now, if this slide comes up, this means you're involved. There's always a question to you. And this is totally anonymously, so I cannot be tracked back who gave what answer. But you will see the answers of everyone. And to join in here, you have to open up on your smartphone or computer, whatever you use, this site here, menti.com, and enter this number. And if you do so, you will come into this, and the first selection you can take is what you like. So that's just a test, training, yeah, an exercise to see that you managed to get in there. Right, and you can just decide, do you like licorice, chocolate, sour, or fruits? Later on in the lecture, it will be then on the topics we're discussing today. So, and I can see that here like 30 are logged in and 19, 20 have selected already. You can see it down in the right corner. And also those who are online joining in can also be part of this. When you run later on the quiz, there will be a timer, yeah? So there will be only limited time to answer. But now it just open. The quiz has not started yet. It's just for trying. And we see 44, 45 people are just logging in. 36 have answered. And yeah, being in Costa Rica, so the majority of you likes chocolate and fruit, I already see. And I'm from Europe. I specifically also like licorice, but there's only one person here in the auditorium who liked that. Okay, we're just waiting a moment until everyone is on board. So there are 48 who are logged in, 43 have answered yet. 50, 44, just give it a moment and then we can start over. Yeah, and then directly the next question is coming. And this is, what is your background? So are you in biochemistry, in bioinformatics? Are you studying bioprocess engineering, chemistry, microbiology, molecular biology, organic chemistry, technical chemistry? So what is your background of the auditorium sitting here and listening to this lecture? So there's, yeah, so 10, and here you can see how many answers. And the nice thing is we can already see that, for example, those who do chemistry, they only like fruits, yeah? So those who do molecular biology, they also go for chocolate. And those are the biochemistry people are most diverse in view of what they use and select as snacks. Okay, so the majority of the auditorium is biochemistry. We have 4 people with background on bioprocess engineering and 3 on the background of microbiology. Okay, so you have found out how this tool Mentimeter is working. And from the next questions onwards during the lectures, there will be several questions during the lecture. We will run a quiz and we will see who's the winner at the end. However, that's anonymously, but you can identify yourself for sure. Okay, so let's start with the first topic. Bioreaction engineering, what is it? That's exactly what we see here. So in the end, you have anything in a small vial where you know there's some activity with a cell, with an enzyme, whatsoever, and this you want to use to make something out of it, to produce something. And for this, you need kind of a vessel, what these 2 homunculus and witches are using. And we all see all the important stuff that we are also discussing today about this, and even more what we're not discussing today because of time limitation. So for one, we need energy input. And energy input comes from fire, from heat below. But we also have energy input by the stirrer stirring the soup. But then this is what we call a batch reaction. We insert everything at time point 0, and then we heat it and we stir it. And normally, in a process, we like to control the temperature, so we thermostat it to have a defined temperature. But then, we're not ending up with this. We run something what we name a fed batch. We're adding something to the system. And this we can see here. In view of time, as the process continues, something is being added. That's what we're naming a fed batch. And then, well, you was also bio background, so we for sure need biology. So that could be the microorganism or the enzyme isolated whatsoever being added to the system. Now the simple question is, if we're running a reaction in there, how can we describe this from a bioprocess engineering point of view? And before starting up with this, we need to talk about the technology. And that is also the big challenge everyone here in the auditorium, including me, have, because we want to have very efficient processes. But if we look how technology has evolved, let's take a look at flying an airplane. 100 years ago, we had a propeller airplane. Maybe there are 5, 6 people seating in the airplane. Nowadays, almost history again, there's this Airbus 380 who could transport over 800 people. Still flying from A to B, but the technology, materials, everything totally changed. If we're looking to chemical industry, one of the biggest processes in chemistry is the Haber-Bosch process producing ammonia. If you look at 100 years ago how a reactor looks like, that's in Germany, it's a BASF company, Ludwigshafen. That's a reactor where the ammonia for is being produced, and this is how the reactor looks like today. There was not this disruptive technology development. And this is a challenge we have to address because we want to move from fossil resources to renewable resources to generate a sustainable world where also our children could live safely in and the children of our children. And therefore, if we're looking how technology has evolved over time and the challenge that there are, if we're looking at the level of optimization, the petroleum-based, fossil-based industry was optimized over decades. But if we're looking at the biofield where we are standing for here in the auditorium, this bio-based, in this bio-based field, the level of optimization is still very low. And that is a big challenge if, to fill this gap and to compete. Is the audio not working or? Yeah.
You need to look.
No, that's fine. Okay. Should I switch something? No. Okay. Yeah, and this is our challenge, that the new systems we're devising, we're developing, so making use of waste materials to establish a circular bioeconomy, for example, to make use of the waste material to produce material that could be recycled, to develop the technology for this. And to be competitive with the fossil-based materials. And if you use the skincare cream this morning, probably around 90% of the skincare cream you have been using and putting on your face is oil from the soil, so fossil resources. The minimum is bio-based nowadays, just as one example. Okay, now how to understand how we can address this. There we need some key fundamental understanding. And this is what I would like to give you in Scratch, very basic, this morning. And if we address something, there are 3 levels we have to take a look at. For one, it's an interdisciplinary field. So there the topics of biotechnology, chemistry, and process engineering need to come together. And if we're looking at optimizing any kind of process, in the first place, we have to look at the catalyst itself. And this catalyst could be an isolated enzyme, could be a whole cell, could be a chemical catalyst, maybe even. And this we need to characterize in terms of kinetics and how's the performance of this one. But this is not naked. This catalyst, this enzyme, this whole cell, is in a microenvironment. And this microenvironment could be just water, for example, could be an organic solvent, could be any surface where I attach it to, could be anything that is changing this microenvironment. And therefore, the performance of this catalyst of the whole cell, if it's attached or included, integrated in alginate gel, for example, or anything like this, will change performance. And this might influencing the performance of the catalyst, and this we need to know to develop a process with this. And then this catalyst with the microenvironment, we need to bring in into an apparatus. And this catalyst with the microenvironment and the apparatuses, there often we end up with multi-phase systems. So we maybe have whole cells in alginate gel, and then we put it in water, organic solvent. So we have different phases which we need to separate and control. Yeah, and therefore we need to understand all these different levels to design an overall process. Now, coming back to the really basics, what we've seen with this 2 witches stirring in the hot pot. How can we describe this? Let's assume we have a simple reaction. We have one starting material we want to produce out of one product. If we are unlucky, and most of the time you're unlucky in research, well, that's a challenge. What makes fun on the other side is that you produce a side product that you do not want to have. Now, this we have to describe. So how much starting material will be converted in our product, how much side product was produced, that we can optimize it, that we can minimize it. And for this, we use 3 terms. And these 3 terms are, for one, the conversion. And now it becomes important because the first question I give you in a moment will also address these 3 terms. What does conversion mean? Conversion is just telling you how much of the starting material was converted away to the product side. But it does not determine how much product or how much side product is being produced. So just asking how much starting material was converted away. And we can calculate this in terms of, that's a sign for conversion, that we have the mole at starting point, time point 0 of the starting material, minus the substrate concentration right now at this time, being left over, divided by the one, bless you, at time point 0. So just asking how much is reacted away. Then the second term we have is yield. And yield is describing how much product we have produced, but now the question is, on what basis did we produce this product? And yield is telling how much product is being produced on basis of the starting material at time point 0, when we put everything in this hot pot at this time point 0. That is what yield is describing. And therefore, yield is how much mole of product produced minus the mole of product at time point 0, normally nothing, divided by the starting material at time point 0. And now we need to learn something about selectivity, because we have a side product we don't want. So we want to know how selective is a product being produced. And that is described by selectivity. And the selectivity describes how much product is produced in terms of what has reacted. Not what was there at time point 0, but how much product is being produced in relation to what has reacted over to the product side. These are the 3 fundamental basic terms, and they are correlated with each other. Namely, the yield is nothing more than the product of conversion and selectivity. Yet with yield, we still have one point we need to consider. The question is, when do I measure? What yield do I have? Because if that is my reactor, and I'm measuring in this reactor right now in here, then I name this analytical yield. I don't see my product. It's solubilized in here, yeah. I hope it's just water, but let's assume there's something in there. And that's the analytical yield. And that is the yield we're addressing in reaction engineering. But other people also use something that is named the isolated yield. This means we might need to extract our product out of this water in this reactor, in this bottle. Then we have a further operation, a unit operation, downstream processing we name it. And this also can have a yield, a different efficiency. Then we would not have a clear differentiation what was produced in the reaction, starting material to product, and what was lost maybe by isolation of the product. Therefore, the yield we're addressing is only the analytical yield in what we're discussing in the following. Yeah, and to this now our quiz will be starting. And now you can join in again. You get a name and a figure, which I cannot correlate to you. I'm just waiting until the number will get steady. So there are 36 players. And then we will start it over. And then we can see which figure does best at the end. But you do not need to out yourself who is who. Yeah, 44, we had around 50 before, so just waiting a moment. And so there will be 2 questions in terms of conversion and yield. And you have a defined time always between 20 seconds to a minute if there are later on more complicated questions. And feel free to discuss with your neighbor prior giving the answer, okay? Okay, 48 players, that seems to be stable, so let's start the quiz. Oops, sorry, that was wrong. I need to press enter here. It's different on this one. We're gaining some players, so yeah. So you will see the quiz as a question on your smartphone or whatever you're using. And the question is, conversion describes what? How much substrate was converted? How much product is formed? How much product in relation to reacted starting material is formed? Or how much product in relation to starting material at time point 0 is formed? Conversion describes what? And you see the time, so there are 15 seconds left over. 49 already have answered, so we're waiting for the last one to come in. And the result you will see at the end, yeah? So during the quiz you don't see any answers beforehand. Okay. Yeah, so we had 21. That was the right answer, the green sign. How much substrate was converted? So conversion is just asking how much starting material has reacted away. How much product is formed is of no interest for conversion. So it can be 100% side product. How much product in relation to reacted starting material? No, that was the selectivity. What was reacted away? And how much product in relation to starting material at time point 0? Well, conversion does not care for product or side product. It's just how much has reacted away. And by the way, if you determine enzyme activity, you might remember it's micromole per minute. That's never addressing how much product is being formed by the reaction of the enzyme or the cell. It's always how much substrate was converted. So that's conversion. Okay, second question. Yeah. So second question. What does yield describe? So yield describes how much product in relation to side product is being produced, or how much product in relation to reacted starting material is being produced, or how much product in relation to starting material at time point 0 was produced. Okay, 1 second to go. Well, only right is the right side, the 18 here. How much product in relation to the starting material at time point 0 was produced? That is the yield. What the majority answered, how much product in relation to reacted starting material that was going over the product side, that is the selectivity, okay? Good. Now, 2 answers to this topic. Now we see who did it best. So you all see the leaderboard, and that's for accounting for right points and quickest answer in combination. And you see the winner so far is Millie, followed by Montana, Chen, Alexi, Ronald, and so on. So, okay, so that will be our competition now running on, and we will see if Millie will defend her position or someone else will come up to win there. Okay, now let's come to a practical example. We do some theory and then we have some practical examples. One key point in industry is, for example, producing this compound. It's a chiral compound with 2 chiral alcohols. I don't know if you know chirality. So this means, just to make sure, it means that if you have, our hands are chiral, they are image and mirror image, but they are not identical. Yeah? So the thumb is on the other side. And this is true also for some chemical compounds, where we for residues on a carbon. And this compound with 2 chiral positions, we can generate classically chemically, but that's not good in view of the non-selectivity. Tells us how selective this was produced, and you see we're 86–70% not good. We can do this much better with whole cells, Lactobacillus kefir cells. And in the end, they do it in a 2-step reaction. We're starting up from this diketone, so this compound with the 2 carbonyl functions which are being reduced. So in the end, it's a 2-step system. And the only thing you need to keep in mind now for the next transparencies, it's an A-B-C system. We're transferring A to B, and out of B comes C. That's the target. So let's see how this runs. We're running a batch reaction. And in this batch reaction, we insert 22 grams per liter of the cells. The cells need some glucose, so we give them 130 millimolar glucose. Then our starting material, it's named hexanedione, and we still maintain pH constant at 6. And the course of the reaction looks ideal, because we have the starting material A is decreased by function over time, so we have 100% conversion of A. Then our intermediate B is being formed and then being consumed, because the final step, B to C, is followed up, and we're forming C in the end. And it's almost ideal what we see here. So A is for 100% converted in C, so we have 100% conversion and we have 100% yield in C. Now, this reaction is not good. Why it's not good? Because, oops. Sorry, something missing here. It's not good because we have a very high mass of cells we use per amount of the starting material. We have 22 grams of cells per liter to produce very low amount of the product in the conversion. So what can we do to do this better? So how can we increase the productivity per experiment? And there's an easy thing, what we already saw in the first picture with the witches, because they added something to the reactor. So we could run a fat batch. So the batch reaction is what we saw just before. So starting material is decreasing and product is being formed. And we just had an additional intermediate. Now if we are adding the starting material, A, or the substrate, constantly to the reactor, we would expect ideally that we constantly produce more product, because the reaction is running so nicely. That would be the idea. So let's do this and see what the outcome is. Here we see this. We have the batch reaction going on. We're feeding A, and so our starting material at a rate of 24 millimole per hour, and something strange happens. We still have the same amount of cells, 22 grams per liter, but something strange. Because what you can see is that the final product C is not the final product we're producing. Somehow, we're mainly producing B, the intermediate. That is strange, because the batch reaction looked so ideal, so nice. What could be the problem? So we have the constant concentration of our whole cells. We have a feed rate given here. And now the question is, what could be the reason for this? However, by switching to the feed, we increase the productivity by a factor of 9. We started up in the standard batch with 0.5 gram per gram product per gram of cell dry weight, and now we are up to 4.5 gram product per gram cell dry weight. But well, to isolate it, forget it, because our main thing we are producing is our intermediate. So what did go wrong? And let's take a look at this, and I've got some ideas what might be the reason where you can think about. So you can rejoin. Six, 7. Okay, and now you can speculate what might be the reason, what we're observing, then we're taking a look if that was true. So what is limiting the reaction selectivity for C? So to produce the final product. Is this either the volume change because of the feed that we're adding there, because of the aqueous feed, or is the feed rate too high? Do we add too much per time unit? Or is the feed rate too low? Do we need to add more per time unit? Or is the applied biocatalyst activity just too low? What do you think? Feel free to discuss with your neighbor. You still have half a minute. Yeah, we have broad distribution. But the right answer, and I will show you this in the moment why this is the feed rate is too high. Why can it not be the other results there? Well, volume change because of feed, right? If we're adding a feed, we have increase with water in the volume, but the concentrations by this will decrease a bit, but the ratio should still be, since we have active cells, still be possible to reach. Too low feed rate, if we would be too low, why should we make more C if we're faster? So the rate, the proteins, the cells must be more active, so this could not be the right answer. And applied biocatalyst activity, yeah, we could also increase biocatalyst activity, but in our experiments where we had the given concentration of biocatalyst activity given, the feed rate was too high. So let's take a look at the leaderboard, and then I explain to you the experiment in more details. So let's see how Millie did and the others. You see, others also have chances. So now the winner so far is Montana, Alexei, MMC, Ronald, etc. Okay, back to our experiment. This is what we started off. The right answer was the feed rate was too high. So let's run the same experiment in lab and reduce the feed rate. So this we do stepwise. Now we're reducing from 24 millimole per liter, reduces to 7.2 millimole per liter, and you see suddenly the system looks totally different. Our target compound C becomes a major product being produced, yield is increased. However, our side product B is still formed significantly. And now we further reduce the feed rate per catalyst activity. You can see we come to a situation that we wanted to reach, that we have a constant increase in relation to our feed, and A and B, our starting material and intermediate, are on a very low level. And this is determined on the catalyst activity and the amount of starting material we give per time unit. And by this means, we increase the productivity by a factor of 9 in the fat batch reaction. So what do we learn out of this? We learn out of this, besides how to control the fat batch, that selectivity is influenced by the feed rate and the concentration of the biomass. And there's a clear correlation. Selectivity is a function of the feed rate per catalyst. So if we have a low feed rate, a high catalyst concentration or high catalyst activity, we can reach a very high selectivity to catalyze the two-step reaction. Okay, this was our first example. Now we are switching gears and coming to a second example. In this example, I would like to talk with you about something else. There are two terms. So far we talked about kinetics, how fast the reaction is going. Now a second term comes into play, thermodynamics. And what that is, we're going to talk about now. The example is we want to synthesize esters. These are fatty acid esters. And if you use some skincare cream with some biological components in there, the possibility is very high that in your skincare cream was polyethylene glycol laurate or glycerol stearate or myrcene myrcetate. If you look on the back this evening, you can find those names in there. And how these are produced, this is done in part, at least at the company Vonik, we were working together with a process we had developed. And I will take you in process design here very roughly, very shortly. One thing is still changing. We were in my water bottle in the experiment before. Now we are working in pure reactants. So we have the pure fatty acid, we have the pure fatty alcohol that we could, for example, also get out of palm oil or different vegetable fruits, plants. And now we're working solvent-free, so in the pure reactants. And therefore, we often have to challenge inhibition phenomenons. We shift from concentration to weight percentages, so X% gram per gram in the mixture. And with this, we take a look at this reaction. Independent of what component we're producing, it's a very simple reaction you most often have in first class of organic chemistry. It's named esterification. So we have an acid, we do have an alcohol, we esterify it, form the ester, that's our product. And then we have a side product, and that is in this case water being split off. Now, what are the limitations if we want to realize this process? The problem is the equilibrium of reaction. That's not 100% on the product side. And that's a challenge. Because if you're a company who is producing the skincare creams, they want to have a very high conversion, larger. The limit is 99.8% conversion, that they can directly use the fatty acid ester in any of their skincare creams. Why is this? Well, if the conversion is not on the right side, you have a lot of acid left over, and suddenly your skincare cream will be itching if you put it on the skin. Then you won't buy it anymore, and the company cannot sell its product. Very easy. So there's a clear goal why to reach high conversion. Yeah, so limitations are equilibrium of the reaction, often sometimes difference in polarity. So if the alcohol and the acid are very different in polarity, we might not have one phase, but multiple phases. We're not going into this right now, but this is one of the challenges depending what product you're producing. And the third one is viscosity. So these materials, often the esters you're producing, have a viscosity which is in the, like honey. Yeah? So high viscosity, 1000 millipascal per second in viscosity measures. Now, the point I would like to discuss with you now is a very simple question. What can we do to increase the conversion to the product side? And I give you just two answers, possible answers. So very easy question, And we will discuss the effect afterwards. So let's switch over. So next quiz question. How can we increase the conversion? Okay, it's around 50 like we had before. Oops, sorry, it was the wrong moment. Here is the button. Here comes the question. How can we increase the maximum conversion in this reaction? Is this by molecular engineering, biocatalyst optimization, or is it by process engineering? One is totally wrong and one is totally right. There's no gray tones here. It's just right or wrong. And why, we will discuss this in a moment. Any idea? I said it's an equilibrium reaction, starting material to products. You want to have 100% very high yield, very high conversion. Okay. Yeah, I know you're from a biochemistry, biomolecular background, but the answer is wrong. You cannot do anything with the tools you have from biochemistry to increase the conversion. Why this is, I will explain you in a moment. But 15 were right, we have to apply process engineering. Why this is, we'll also see in a moment. Let's first take a look at the leaderboard. No? So who made it up now? Accumulating all the points, so, and the rate, so Alex C is now up on top, followed by Montana, Winter, Ronald, Josue, and so on. Okay, switching back. So what's going on here? Well, in the end, this morning I set off at 7:30 in Heredia to come to Carthago. Long trip, lots of traffic, okay? In the end, that's already the explanation. The target was Carthago. And I could have selected a nice red Porsche I do not own, just to stress the fact, I would like to have, yeah? Or I could have, I would assume, almost use a bicycle. They are totally different in rate, okay? If I would start it at the same time, I would have made it over here because the finish is Carthago, okay? Now, looking at the weather, maybe it would have been nicer to go to Puerto Viejo at the Caribbean coast. So let's start over right now here. The aim we can shift. And the aim is determined by thermodynamics. If we shift now the aim from Carthago away to Puerto Viejo, the finish will be given. If I increase the rate of the catalyst by molecular engineering, for example, I will just be faster there. Yeah? So if I have a faster car, I will be faster at the end of the traffic jam. But it will not alter anything with a traffic jam. I just need to get more roads to get rid of the traffic jam. And that is the interplay between kinetics and thermodynamics. With kinetics, with molecular engineering, we can make the catalyst faster, but we cannot shift the thermodynamic equilibrium. The thermodynamic equilibrium we can just shift if we work on the product side. So we remove something, we pull or we push the system. We cannot push here because this is a 1-to-1 ratio of our reactants in there. So we remove water. And by this, we let the equilibrium follow the removal of one of the products on the product side. Well, water is our side product, our real product we want to sell as the ester. And by this, we're shifting the equilibrium. So how does this translate into any application? And we can have a higher temperature. You know this, if you have honey and you heat it up, it becomes more liquid, for example. Also, this might help. Now, what are typical reactors that we can apply here? It's, for example, one stirred tank reactor where we draw vacuum overhead. So we have simultaneous water removal with a vacuum and the reaction there in the liquid phase. Then we could have what was in place at Evonik at the time being a circulation loop reactor where we have a stirred vessel where we draw vacuum overhead to remove the water. And then we have the enzymes immobilized in a packed bed in a continuous flow setup. And we're pumping over this. But the limitation there is that this does not function with viscous media, what we have if we would use fatty acid esters for skincare. And because if you pump honey over a chromatographic column or a fixed bed in your lab, you know that will be difficult. You have high pressure buildup. So no way to go. And therefore, what we developed for this application is bubble column. So where we have the mixture in here and we rate from the bottom and then pass the gas through the column, strip out the water with the gas, and by stripping out the water with the gas passing through, we shift the reaction equilibrium to the product side. That's the trick. Yeah, and how looks this like in the lab nature? So this is a 2 meter high bubble column, for example, in our lab. And let's skip this. I'm running a little bit late. I don't. And how this functions efficiency, I will show you on the example of producing the myristoyl myristate. The enzyme is a commercial enzyme. You can buy it, can the Antarctica lipase B under the trade name of Novozymes. And now the product, ester, what you find in skincare cream is low viscosity still, so 6 millipascal seconds. And in the end, we have a 4-phase system. We have the liquid phase made out of the starting materials. Then we have the catalyst that's immobilized on a carrier. It's a solid, so like peppercorns you throw in there. Then we have the gas, bubbles passing through, taking up the water into the gas phase. And we have a little bit water as droplets in there that we hopefully remove because of the reaction. And now we would like to compare the performance in terms of every 3 reactions we're running. All started up with fresh enzyme, which haven't seen any reaction. We know they are comparable than these reactions. And so we have for one, the stirred tank reactor, the one on the left, where we draw vacuum overhead. Then we have the circulation loop reactor with the immobilized packed bed. And then we have the bubble column. And then we see how the performance is like. And now we see here conversion. You already know what that term is, as function of the reaction time. And on the right side, we see the result with and that's just the last 2%, 1.5%, because the customer where it's sold to formulate the skincare cosmetics needs 99.8% conversion. And the question is, how fast can we reach it? And now you can see on the right side, it's the stirred flask with vacuum overhead. The purple one here is the fixed bed, the circulation loop reactor. The green one is a bubble column. And the dotted line on the left one, that is the theoretical value that could be reachable, but not accounting for any mass transport limitations in there. So the best one is the bubble column in performance. And so the reaction time in comparison to the already established processes at the time being is cut by more than half. Yeah, so I hope I could demonstrate you with this example that in the end you need to have an understanding of kinetics and thermodynamics at the same time point. And this is not true only in designing this process, also if you do in a small Eppendorf cap or any small setup with any microorganisms or enzyme, a reaction, you always have to ask yourself, what is the limitation? Is this the rate or is it thermodynamics? And then you have different approaches, what you need to do. And this is now the larger scale version. This was the 2-liter bubble column in our labs. That's a 200-liter trial in Germany that was set up of pure reactants already at Nevonic site. And nowadays, it's in production for one Asiatic region as well as in Germany. Yeah, with this, I'm coming to the last round of examples. I think we have until 11:30, or? Yeah, okay. Perfect. So yeah, we're coming to the last thing, and everything we did so far was just playing around with my bottle here. Yeah, that's a batch reaction. We added something in terms of time. That was a fat batch. Then we had our batch reaction where we were bubbling from the bottom, gas in and getting gas out at the top. But we never let our reactant phase continuously pass through the reactor. So we never had a continuous operation where we continuously added starting material, where we continuously withdraw products. And there are also some tricks of the trade. There are some principles I would like to discuss with you right now. And the oldest example, the first application of a continuous reactor with a biotransformation, comes from 1916, so long time way back, over 100 years, published by Nelson and Griffin, because they immobilized invertase, an enzyme that splits sucrose on charcoal. And they packed it in a column. It's a very old picture here. They didn't have a pump, and so they just put the water with the sucrose on a higher level, and then let it just flow by gravity through the column. You always let it flow from the bottom to the top in this operation, because if any bubbles formed in there, they are drawn out to the top and not trapped in there. And this was academic publication. And then in the First World War, this process was even actively produced in production, because normally the splitting large scale is done by sulfuric acid. And sulfuric acid was short because of weapons production. And so they remembered the publication by Nelson Griffin, and for the time being, they use this continuous operation, large scale, for production. However, it was said, I never tasted it, that the glucose-fructose mixture you generate out of the splitting tasted better if you use sulfuric acid. So after the war, they switched back to the chemical process. There are many other large-scale biotransformations, but this is one that still run chemically large scale. But that was the first continuous one. Okay, now what we're talking about in the following, and where we're playing around and do some quizzes with, are reactor types. And the first one, the batch, we already know. Just to repeat, we have concentration changing as function of time in the batch. And so starting material is consumed, product is being produced. That's what we did so far. Now we have to take a second look at this reactor. That's important to understand the other reactors. And that is, how does it look like in space? So let's say we're sitting down here on the left corner, or we're sitting up there on the right corner. How does the concentration being changed in one place with time? So if we're in one place, then the reaction, at different locations in the reactor, we will have, if assuming it's ideally mixed, we will find the concentration at the beginning of the starting material everywhere identical. We have well mixed, the concentration should be identical in every place in the reactor. Now, as the reaction proceeds and we produce more product and starting material is consumed, the starting material should be decreased at the different locations, everywhere identical at a given time point. Okay, I think that's clear for everyone, right? Perfect. Now we have the following. If you're thinking about continuous production, continuous synthesis, two fundamental types of reactors. One is a so-named plug flow reactor, and the other one is a so-named continuously operated tank reactor. The plug flow, that's the one from Nelson Griffin we just had. Yeah? So we pack in here, for example, cells immobilized on resin or enzymes immobilized on resin, pack it in a column like a chromatographic column, just that we have our cells or enzymes tracked in there. And we feed our starting material at the inlet, and at the outlet, hopefully, our product comes out, if everything is right. The question is, how is this performed? So, easy, if we take a look at this place in the reactor. So, starting material very high in the beginning, and passing through the reactor, the starting material is consumed, and we produce to the end the majority of the product. This means, and this is an important point now, this means over the length of the reactor, we have a high product concentration, but only in the end we have the maximum product concentration, and the concentration here at the outlet of the product we only find here. We don't find it somewhere else in the reactor. Only at the outlet we have the highest product concentration. And starting material is decreasing. If you add one place in the reactor, you can see that in one place at a given time the concentration will not change. So if we're here, we will always have the same concentration. So at x.0 at the inlet here, it's always a maximum starting material concentration. At the outlet, always a maximum product concentration, because transformation is performed over the length. Totally different, this is in case of a stirred tank reactor continuously. Because here we also continuously add starting material, and we continuously remove product or liquid. And now we can retain in this reactor also our cells or our enzymes. Either we immobilize them and have them just as heterogeneous balls in there, we're retaining with a net, or with an ultrafiltration membrane, where with a membrane we can retain solubilized enzymes or cells. So also the cells or enzymes are in the reactor. The big difference between those two is that in the continuous stirred tank reactor, we operate the whole time under maximum concentration of the product. So what we measure here at the outlet, we will find all the time, every point in the reactor. And that is true for time and for space. So we're always operating in the reactor at minimum starting material concentration and maximum product concentration. Sounds simple, but has humongous effects if we're thinking now taking a reaction running in here to continuous operation. And what those are, we will think about in the following also on examples. The first question I would have, if you know for sure something's running safely in your batch reactor, you're getting 100% product, everything is great, you optimized your enzyme or your cells, and you might have installed even shifting the equilibrium, everything is great in here. Which one would be the continuous reactor you will be choosing? So which one is the continuous variant of the batch where you can directly transfer it without any thinking? And this is the next question I have for you. So we're going back to Mentimeter. So waiting for everyone to join in. We had almost 50 before, just waiting a moment. Okay, around 40 stays, then we take that number. So, question: is a continuous variant of a batch reactor from reaction engineering point of view? What is this? Is this a fed batch, a CSTR, continuous stirred tank reactor, or the plug flow reactor we've seen? So which one might be the continuous variant? We can safely transfer the performance of a batch reaction without any thinking. Yeah, that's the most common answer you always get, and therefore I ask this question to sensitize you. The continuous version of a batch reaction is the plug flow reactor. And why this is? Because the performance is identical. I will show you in a moment when we take a look at this again, but let's take a look at the leaderboard first. You see, everyone has a chance to make points here. So far, Alex C staying up, Montana, PH, MMC, Winder. So PH is new coming into the play there. Okay, let's take a look why this is. No? Somehow it's blocked. Okay. So, what is the learning point? The plug flow reactor, that is the continuous version. Why this is? Coming back to this one, we can say that if you look at the profiles, just the time and space are exchanged here between batch and plug flow reactors. The performance overall is identical. You always come from a high starting material concentration in the reactor to a high product concentration. This is decreasing gradually over time. In the continuously operated tank reactor, you're always at the top concentration of the product. And you're always at the minimum concentration of the starting material because this is well mixed. And if we pump through here, and let's assume this will take 1 hour to pump through this reactor, everything they add every minute is directly converted so that we are constantly at this high outflow condition. Therefore, we are also saying this reactor is operating under outflow conditions, so meaning the concentration we're measuring at the outlet, we will find it at any place in the reactor. In contrast to plug flow reactor, with the outflow concentration, we only measure there and nowhere else in the reactor. Okay? Okay, now let's take this one step further. We do some brain jogging here. Oops. Oh, that comes in a sec. So first question to what I explained just before. Next question. Okay, back to 40. So the first question addresses the outflow conditions. In the CCR, what do these term outflow condition mean? What does this term mean? Does it mean concentration of the reactant at the outlet is identical to the one at the inlet, or the concentration of the reactant at the outlet is identical to the one inside of the CSTR reactor? Or does it mean the concentration of the reactants at the inlet is identical to those of the inside? What do you think? Yeah, the majority has it right. That's good. Right. The right answer is what we measure at the outlet is that you find everywhere because it's continuously stirred in the reactor, and the other two are wrong. Next question we still have here. Let's assume we have now a product inhibition. Yeah? So the rate of the reaction is inhibited by the more product is limited, the more product we form. That's product inhibition. Yeah? So one of the standard cases we are talking about Michaelis-Menten or monokinetics, you can have product inhibition. Okay, that's the next question. The question is, what reactor would you choose? Very simple. No, which should not be used. So let's assume you have a product inhibition. What reactor will you not use in case of a product inhibition of these two continuous variants? will not use. Is this a CSTR, continuous stirred tank reactor? Is this a plug flow reactor? Or is this a batch reactor? Only one you will not choose. The other one you can choose. And you can just play with the profiles you have seen before. You can also simulate, write differential equations and whatsoever and to calculate this. But the principles that we're talking about today, you can deduce from these simple graphs I've shown you. Okay. What you will not, yeah, perfect. No, it's not perfect answer, sorry. What you will not use is CSTR. You will use a batch and you will use a plug flow reactor. Why this is, I explain you in a sec. Let's take a look at the leaderboard. No, come on. Yeah, so this has changed now. Montana, MMC, Mappa, Ronald, they are the leading stars here. Well, why is this? Coming back to these plots. These are the principles. Product inhibition. The only reactor where we have the highest product concentration all the time is the CSTR. In a batch reaction, we're starting up with a majority of the starting material, which is being consumed, and we build up product by time. In a plug flow reactor, identical, just a continuous version of the batch reactor, what we see here, we build up over the length of the reactor the product and decrease the starting material concentration. So the highest product concentration we always will have in the continuous stirred tank reactor. And therefore, the answer was right of those who gave it. The CSTR we will never use in case of a product inhibition, because there we will be the slowest. Okay. Next brain jogging topic, and then we just have one example left over. Now, remember the beginning. We talked about selectivity and yield. And we have a simple system where we have one molecule of A reacting to one molecule of P, or product. That's what we want. However, unluckily, two molecules of A, of our starting material, is reacting to side product we do not want to have. Okay? And now, because of the different profiles of the reactors, if we calculate this, we can express the activity in terms of production of the product as function of the conversion for our two continuously operated reactors. And you can see if you choose the wrong reactor, you will lose over 30% of product. The unlucky thing is, I forgot which one is which, and you need to help me. So one is a line of the plug flow reactor, and one is a line of the CSTR. And that will be the next Mentimeter question. So, bless you. Which is the better reactor for the system? And you can just think about these principles, just the graph we saw before, the performance, the difference between a plug flow reactor and the CSTR. The CSTR was operating continuously, highest product concentration. In the plug flow reactor, we're setting up the product by time, and we have a similar behavior for the starting material. And you see, the side product is initiated by a high concentration of the starting material. Okay, switching over to Mentimeter. The question to this. Last question, almost the last question coming up. Okay, around 40 we had before. So in this parallel reaction, what continuously operated reactor is the best one you can choose? So which gives the highest selectivity and yield? Is this a plug flow or the CSTR? Feel free to discuss with your neighbors. For the side product, you need more starting material. For your final product you want to reach, you need less. Okay, 13 seconds to go. Waiting for someone still to give their answers. 5 seconds. Oh, it's a fit, but the right answer is a majority, slightly, but no less. Okay, the CCR is the right answer. Why? Let's take a look at it in a sec. First, take a look at the leaderboard again. So let's see how it's changing. So Montana is defending position 1 with LXC, Joshua, PH, MFC, Mappa, and so on. Okay, switching back to the reaction. Yeah, so CCR is best. Why? Because, let me click back to this one. Why? Because in the CCR, we have the lowest starting material concentration all over the time. In a batch reactor, in a plug flow reactor, we always start at the inlet with the highest concentration of the starting material. In consequence, we will produce more side product. In the beginning of the reactor, we cannot get rid anymore, which is running through. And this is not happening in the CSTR, in the continuous stir tank reactor, because there we are on a very low level all the time in view of the starting material. So you see, without doing any calculations or so, just by using the principles, you can save a lot of time in running mathematics, just understanding and applying the principles to decide. And the details you need to do then later on mathematics and modeling. Okay, last example for today is out of our lab. What happened to a PhD student in my lab? We have one reaction sequence once again, and the sequence is 2 molecules of this benzaldehyde are catalyzed by an enzyme. Benzaldehyde is an enzyme which is catalyzing CC bond formations and splits. So 2 molecules of this forms an intermediate named benzoene, and then with addition of another aldehyde, it forms the final target. Details of the reaction, what chemicals and so, we do not need to know in detail. Let's say just ABC again. The important message that you need to know for the following is that this intermediate has 2 aromatic rings and therefore very low solubility in water. And you're running this reaction in water. Therefore, DMSO, organic solvent, co-solvent is added. That's not forming a second phase, but is also solubilized in the aqueous phase in water and increasing the solubility of this compound up to 1.4 millimole per liter millimolar solubility. Now, we're in a batch reaction. Like in the first example, we had A, B, C system. And we can see in the batch, very nice performance once again. Starting material is decreasing with function of time. We form the intermediate here. And then finally, we form our product, like the first case. Looks great, right? So now we want to run this continuously. And he was lucky, because this enzyme, the benzaldehyde lyase, has something, I don't know if you know this, is a hexahistidine tag. So where you can easily, so in the protein structure, 6 histidine molecules added so that you can easily grab it with affinity chromatography to immobilize it. And so the enzyme was easily immobilized, and he thought, hey, great, let's run a plug flow reactor, packed bed reactor. I can just, and then I've got my continuous synthesis, because I told you the batch, the continuous version of the batch is the plug flow reactor. So everything should be great, right? For the following discussion, keep in mind, maximum solubility is 1.4 millimole per liter of this intermediate B, of this one you can see here. Okay? Now, He's lucky, everything runs. He set up the column in the morning, and yeah, then we went together for lunch, and you could hear a cry out of the lab. Because when he returned from lunch, what he saw was this. This is the column with the immobilized enzyme. The pump had stopped working because of overpressure. And here in the beginning, there was some, and this was operation, so inlet here, outlet there, you see white stuff in there. Something, color has changed, doesn't look as it is expected to look like. And my question in Mentimeter is, I give you 3 possible answers in a moment, or 4, I don't know. What is the reason? What is our problem? And then we talk about how we solve it at the end. And the solution you can already see here. So ABC system, maximum solubility of the intermediate is 1.4 millimole per liter. Here you see the course of the starting material A, the course of the intermediate, and the course of the product. You have to take a close look. Okay, now up to Mentimeter. What might be the problem? Okay, we were around 40 before as well. Yeah, so let's start. So what is the problem in this process? Is it either the biocatalyst was deactivated, or the reactor has cooled down, leading to precipitation, or solubility of the intermediate surpassed, so of B, the solubility was over exceeded, or the flux was too high, you were just pumping too fast through the column. What might have been the problem? And you could see the solution, the answer already on the transparency before I discussed with you. Yeah, perfect. The majority has the right answer. The solubility of the intermediate was surpassed. We'll see in a moment. Flux could not be too high. Why should it be blocking there then, or precipitating? Reactor has cooled down. Then there need to be an exothermic, endothermic reaction. Endothermic reaction, I didn't tell you anything about this. And biocatalyst deactivated, I should have told you. Let's take a look at the leaderboard. And that is also the final one. So the final winner as of today are Montana, followed by Alex, Jose, MMC, Mapa, Ronald, and you can see your own location, position on your smartphone. Okay, what was the reason? Well, in the end, I told you 1.4 millimolar, and with any scientific data, you have to take a close look at the data, and you can see that intermediate being formed here in the beginning is at 2.5 millimolar. So this means that in the end, in your batch reaction, precipitation has started because you're surpassing this maximum solubility of B. In a batch reaction, you don't care, you just keep on stirring, and then it is continuously converted to the product. But in the column, since we said the length axis, if we have the inlet here and here, we have always the same conversion at the same time point. So we're accumulating more and more of the compound, especially at this given position. And that, therefore, the majority of you had the right answer. Now, last point, what can we do to solve this? Well, in the end, there's a trick. We can transform a plug flow reactor to CSTR operation, and that's very easy. We just add a pump, and this pump needs to run in the cycle just 20 times faster than going through the reactor. So we are stirring with a pump, so to say. Then we have CSTR performance, and if we're doing so, then you can see after a short time, we have a clear column. So everything is solubilized again, and we're moving to constant product production with minimum starting material concentration as expected. Because CSTR, as you remember, is always maximum product, final product concentration, minimum starting or intermediate concentration. Yeah, and with this, I'm at the end of today's lecture. I hope I could demonstrate you that the different disciplines need to come together. Try to think in simple principles to understand the systems itself prior starting with detailed lab work or with detailed calculation, simulation. Think in the simple principles so that it does not happen what those guys happened, namely talk to your neighbors, talk to your coworkers, brainstorm together, find together a solution. That is a way for the future to go ahead. And therefore, chemistry, biology, and engineering need to interact to come to a final solution. And my take-home message for you is always differentiate reaction, yield, and isolated yield, what we had in the beginning. Consider thermodynamics beside kinetics when optimizing. Think about the esterification reaction, the skincare cream production. Continuous version of the batch is a plug flow reactor, not the continuous stirred tank reactor, what most assume in the first place. The CSTR operates under outflow conditions. Consider the influence of the reactor type on reaction selectivity, as seen in the last example, or the ones we discussed before. And keep in mind, always bioreaction engineering needs to be complemented by molecular biochemical engineering. So those need to play together, and it's important to learn to speak languages of the different fields. And I hope this was a motivation for you to do so in the future, if you're not doing so already, to talk to your colleagues also from other disciplines and to learn from each other. And the examples I've shown, nothing I do myself, except giving some lectures. So this is a team of the institute, and you might know, can identify maybe this face, that's Jose, who studied here and who's doing his PhD right now in my institute. Yeah, and these are the collaboration partners we're working with, who financed all this research. So thank you very much for the invitation, and if there are any questions, I'm still open for this.
So thank you very much, Dr. Lise, for your talk. Thank you all for attending. Is there any question you would like to ask, now that we have this expert here with us? Well, if you need some, there you are. I was just breaking the ice, but I can ask later, okay. No problem.
So when you said that we can switch from the BFR to the CSTR, like to fix that problem, so we already have the highest starting concentration possible. So when we switch to the CSTR, it is not optimal, since that one has to start with the lowest possible, right? So when you said that we can fix it that way, you mean like if it already happened, we can fix it like in the moment? Or you mean like completely like redesigning it and starting from scratch? Like if it happened, like physically, I already have this problem, how can I fix it? Like, should we switch to the CSTR like right away and it eventually will, let's say, the concentrations will be fixed? Or should we just like scratch everything and start again?
Yeah, thank you very much for the question. Good question. Any question is good, so not to differentiate there, sorry. The point is, well, it's just really adding one pump, yeah? And the setup, the pictures I've shown you is just by adding one pump and pumping 20 times faster in the cycle, not a total different setup. Now, the point is, what you were asking is in view of starting material concentration for the different reactor types. Both reactors, the plug flow reactor as well as the CSTR, we're starting up with the identical starting material concentration, both high concentration of starting material. But the difference is that in the plug flow reactor, over the length, so if this would the XY axis, we would start up at a high concentration, what we see here, and over the length, the starting material concentration will decrease, okay? In this tank reactor, we do not have, this length axis, We just have different positions. And now, let's assume we need 1 hour, normally it's much faster, just for imagination, We need 1 hour from the inlet to the outlet passing through here. So in this 1 hour, we're decreasing by time the starting material concentration from the high level. In this reactor, in both reactions running, here we are also running the reaction the whole time we're stirring. Now we're adding continuously high concentration and have the outlet. But this is also stirring for 1 hour as well as we pump through here for 1 hour. And now if we add this minute, the next minute, the third minute, the fourth minute, the starting material, it's a high concentration level, we will directly transfer to the product. This small amount we add here. And therefore we're dropping directly down to a very low level, constant level of the starting material, and maintain at a very high product concentration level, in contrast to plug flow, where it's over the length of the reactor in this 1 hour, and we're maintaining longer time at higher concentrations of the starting material. Understandable? Thank you.
Anyone else? No?
Well, first of all, thank you for the talk. It was very, well, informative and useful.
Thank you.
How long does it usually take from, for conceptualization of a reaction for a certain product, like the one from Evoke, I think the company was called, to lab execution and then incorporation into the industry and all that product side?
Yeah, also a good question. It really depends. It's not a question of a week, a month. Normally it's a question of years. So, with this skincare cream example from Evonik, this in the end was, something like 5 years. So 1.5 PhD until they started it in production larger scale. You first need to break the ground. You need to know the kinetics. You need to know the thermodynamics. This you need to determine. And then if you really decide to scale it, then you also need to see if there's a market for the product. What are the competitors doing? It's not only what I talked about, the process engineering or the enzyme, the molecular engineering. It's also what I didn't talk about today. So it's also what's the markets? Do I have competitors? Is he going to sell the same product? I heard about this maybe next year. So I have to evaluate what technology is he using? What are my chances? Where do I get my raw materials from? Do I have a safe supply of raw materials for the future, and so on? So a lot of questions need to be clarified, but just from the lab science, what your question I think was more addressing, I would say it depends, but normally you can calculate some years.
There is a concept we've been discussing in class that you were somehow including in your talk, the Michaelis-Menten constant.
Yeah.
I'm hoping they can answer this, but maybe you can help them just in case. How can you relate this concept to these examples that you were mentioning?
Yeah. Well, what I did not discuss, that was a question to them, or?
No, it was, I'm asking them next week. So I'm asking you today. Yeah.
Well, what I did not discuss with you is how expensive are these reactors to operate? And let's forget now the specific example. Just take these 2 continuous reactors. you had the concept already of Michels-Menten, right? Okay. Now, everything I explained to you was a plug flow reactor and the continuous stir tank reactor. And if you want to make the product in 1 hour from inlet to outlet, leaving the reactor, which reactor is more expensive in view of the catalyst cost, in view of the enzyme costs? So where would you need to invest more enzyme? What do you think? One is cheaper and one is more expensive. And this you can answer with the Michels-Menten kinetics, also standard principle again.
Probably the CSTR because it's continuous. So there's
Both reactors are continuous.
enzyme. I don't
Both
know.
reactors are
You know?
continuous. Both is the enzyme. But which might be more expensive?
I would say it's the CSTR, the one that's more expensive because there's an outflow of enzyme, where in the PFR we have the enzyme that's immobilized.
Sorry, yeah. It's a good point that you have, and you're right, what you see here. But for the comparison, we need to compare that we have the enzyme also trapped in here, okay? So in the end, we have either here in filtration, a membrane filtration or so with homogeneously solubilized enzyme, or we have also the immobilized enzyme, we just stir in there and have a filter at the outlet. That would be now the comparison. Sorry, that was not clear from my side. But you have an idea anyhow?
That changes things.
Okay, you have to think about it first. Well, in Michels-Menten, what is plotted? That is rate as function of what is on the x-axis in Michels-Menten plot. It's a substrate concentration, right? Do you have something to draw here? No. So in Michels-Menten, you have, just the, wait a moment. Yeah, that's, if the x-axis here is the substrate concentration, starting material concentration, yeah? And you have here the rate. In Michels-Menten, you have this hyperbolic plot. Yeah? And then you have the two kinetic parameters, Vmax and Km. Vmax was the maximum rate. And in the Km value, that's a specific concentration of starting material you need, that is half, where you reach the half maximum rate. So if you have this course, and you get the half maximum rate here, you go to the curve and go down, that's the Km value. Yeah. Now the crucial question was, how can we correlate this? And the question is, which reactor, continuous reactor of those two concepts is more expensive? And the answer, just to keep it short, come on. In the plug flow reactor, you're operating it for a long time at high starting material concentration, and then you decrease with time. In the CSTR, continuous stir tank reactor, we're operating the whole time as a very low concentration of starting material. So if you have Michels-Menten plot again, yeah, this hyperbolic form, so in the plug flow reactor, you're operating for a long time up on the right corner of the curve, yeah, in the maximum and the Vmax range. In the CSTR, you're operating there in the fountain, in the origin of the plot. So low rate. Meaning, if you want to reach the same conversion point, the same amount of compound to transfer, since you're at a low concentration here of the starting material, even if you have the high inlet, you need much more enzyme to generate much more activity to generate the same performance in 1 hour. Yeah, that's the intercorrelation of Michels-Menten with these concepts.
So maybe good that I ask you today instead of them.
Yeah, but that's a learning curve. And I think that's exactly the point. Yeah, so important is not to learn any detailed values or so. You need to understand the principles, because also nowadays with AI, artificial intelligence, there's so much possible. You can calculate in seconds any kind of humongous models, mathematical models or whatsoever. But if it's right what gets out of these models, you never know, yeah? So also artificial intelligence does errors because it's just calculating on probability who has the highest probability in the answers. But it might not be the right answers. And to prove this, and to prove if any results other people offer you, it's always important to know the principles, that you can quickly judge with the principles, is this the right direction of the answer? Because you are also educated here at the university, at the Tech, which is an excellent university, you're educated to become leaders one day. Yeah? You have other people who might demonstrate you any results. And you're sitting on the one side of the desk, and maybe a lab coworker comes to you and gives you any kind of a plot like I gave you here. And then you don't have the time to redo the experiments to see if you can trust or not trust. You do not have the time to redo the calculations. You have to judge by your education, by your knowledge, by your competence, if this might be true or not. And to do so, you need these principles. And to combine the principles of the different disciplines, like what I told you here on the example with the reactors, and then the more biochemical principles like the Michaelis Menten. And by this, you can then form a picture for yourself.
So thank you again very much
You're welcome.
for your talk and also for this very wise message, last message. Please let's thank Dr. Lise once more.
Yeah, thank you very much for actively participating and staying here. And thank you for inviting me.
Sí, sí. Wow, qué bien. O sea, Professor Lisi, noch einmal vielen Dank hier zu sein und vielen Dank für diese gute Lesson.
Ist mir eine Freude.
Okay, für die Stunde.
Thank you.